Hi, class. As I mentioned earlier today in our review session, there was a couple problems that students requested I make a video for the review, how to solve them. And so I went ahead and prepared all these problems, and I'm going to solve them for you. So if you aren't interested in seeing the particular problem that's on the screen, that's fine. Just fast forward through the video until you see the problem that you requested come up. So starting with this first question. Problem 5, we want to solve a quadratic equation. And quadratic equations, there's 4 ways to solve them, right? Remember quadratic equations. So we can solve them 4 ways. Option 1 is to factor, to solve these by factoring, and that is where first we have to get it equal to 0 like it already is, and then we try and factor that left-hand side, so then we can use a zero product property and set each factor equal to 0. So factoring is a good way to go. It's typically pretty fast if it works. Then we also have the square root method. And this one we have to have our variable quantity being squared. So I'm going to have something stuff with my variable which is being squared, and that's equal to a numerical quantity. So that's kind of the key part about that particular method is I can't apply the square root to undo my power 2 unless all my variables are within the item that's getting squared. In this instance, for this first problem, we can see that method's not going to work. So I can kind of like think of crossing that off my list. So factoring maybe, right? Potentially, we haven't tried it yet. Square root method definitely won't work because although my x is squared, I also have this 6x. So it does not fit our definition of when we can use that. So that would be our second option. Third option that we talked about was completing the square, which you can always do, but one thing that we saw in class is it's kind of a more tedious method. You have to know all the steps. And maybe probably not the fastest either. So this one I'd say is a maybe. If no better option presents it, we could try. And option 4 is the quadratic formula, which also works for pretty much all quadratics. The one thing is, it's also a longer method compared to, say, factoring, and we have to know the formula. So 3 and 4 are more powerful methods. They'll be usable for any quadratic equation, whereas factoring only works for some, whichever ones we can factor. But they're longer, right? We don't want to waste that time on a test. So let's look at this one, pretend like it was a test question, and see how we would approach it. So of my 4 options, I want to go for the fastest, and the fastest one is definitely going to be factoring. So let's try and factor this. So I see a trinomial, so we know trinomials factor to 2 binomials, and that would be the way to go. However, you always want to look for a common factor. If we have a greatest common factor that we can pull out, we want to do that because that's going to make our numbers a lot smaller and a lot easier to work with. And here we do have a greatest common factor, it's 3. So I could pull out that factor of 3. So what would be left here? I'd be left with my 3 would divide out, leaving x squared. I would divide out my factor of 3 from 6, leaving a negative 2, and divide out my factor of 3 from 12, leaving a positive 4. And so that 3 would technically carry down to any future steps unless we divide it out or do something to remove it from our equation. So I'd be left with also a trinomial that could factor to 2 binomials. And I might start trying to factor this. So x times x would get me my first term, the x squared. But here we run into a little bit of an issue in that I'm looking for factors of 4 that add to negative 2. And I really only have 2 possibilities. I have 4 times 1. And because I want to add to be a negative quantity, but multiply to be a positive 4, both of my signs would have to be negatives to accomplish that. So negative 4 times negative 1, yep, gets me the 4 I want, but when I add them, it gets me a negative 5, not the negative 2. So I would know that's not the correct route to go. So what else can I do for factors of 4? Well, all that's left is 2 times 2. That gets me the 4, but again, I don't get the negative 2 for my x term. I get a negative 4. So we've tried all the possibilities, none of them work. So factoring we can't do, right? It's not factorable. So what's left in my list? Well, factoring won't work. The square root method won't work because it doesn't fit that particular format. So I'm left with completing the square or quadratic formula. And between those two, if we had to think of kind of benefits and drawbacks, if you know the quadratic formula, if you have that memorized, that's going to be definitely the way to go. It's perhaps a little bit more fast method compared to completing the square, and we don't necessarily have to know all the steps as much. We're really just plugging numbers into the formula. So between those two, I would try the quadratic formula probably first, and I think most people would agree with that. So let's see what I had. So I had 3 times the quantity x squared minus 2x plus 4. And one thing I can do, I factored out that 3 to try and make my factorization easier, and that was good. But I can also use that for the quadratic formula, that I don't really want this extra factor of 3. So one nice trick that we can do is divide out that greatest common factor. Right? My 3's would divide out, leaving x squared minus 2x plus 4. And 0 divided by 3 is still 0. So all that we really did is we pulled out this extra factor of 3 from the original and got rid of it, right? We don't really need it. And if you tried it both ways, if you tried the quadratic formula on the original with the factor 3 left inside, and then if you also tried it on this reduced quadratic that we removed the factor 3 from, you're still going to get the same result in the end. Just numbers when we put them in the quadratic formula are smaller, right? And smaller numbers are always easier to calculate, so why not use them? So if I use quadratic formula, the big thing is I have to write it down for the person reading my work. They need to know where that came from, right? Why I did all these operations. So writing the formula is actually a really crucial step of work. So I wrote down my formula, and then we want to plug in my values for A, B, and C. I think it's kind of helpful to identify my A, B, and C before I use quadratic formula because, sometimes you're looking back and forth and you might put down the wrong number. So my A, that is the coefficient of x squared. Here it's an implied 1. My B is the coefficient of x, so here it's going to be negative 2. And my C is my constant term, which is 4. So I just find it's helpful to write that out before I plop it in to the formula. I also think it's helpful anytime you're doing formula stuff or just replacing a kind of like variable value is to just put it by default in parentheses. If we do that, we're going to avoid some issues with things looking like they should be a change of sign if you have a negative number, things of that nature. So here my B was negative 2, my A was 1, and my C was 4. And we just want to do this calculation and clean it up some. So my double negative will go to a positive 2. Negative 2 squared will get me a positive 4. And then I like to do the multiplication of the 3 numbers separately. So 4 times 1 times 4 is 16. And I only have one negative sign. So it's going to stay negative as a result. And 2 times 1 on the bottom gets me 2. And then the last step is to really figure out what number do I have left inside my root, what we call the discriminant, right? So 4 minus 16 gets me negative 12. And hopefully I'm recognizing, oh wait, I have a negative inside my square root. And we know that that lands us into the realm of the complex numbers. So we can reduce this. The trick is we're going to pull out the negative 1 so that it'll become an I. And then I'm also left with the square root of 12. And any square root, we want to reduce that square root as far as we can. And so one trick I showed you guys is that factor tree. So I can look for essentially the prime factors. So what would this could break down to 3 times 4. And you could have done it differently. You could have done 2 times 6, and it'll still get you the same prime factors. And then how this works is I want to reduce my root. Since it's a square root, I'm undoing a power 2. So if I see 2 of the same numbers or same factors, that's a square, right? This guy right here is 2 squared, right? So all these numbers are technically underneath my square root. So technically this is 3 times 2 squared, Well, the 2 squared part, we know the power 2 and the square root undo each other. So that's why when you see that pair set a factor, I tell you guys pull it outside the square root, because it's that power 2 that's essentially being undone by the square root. And then any factors that don't have power 2 or don't have a pair up here in the factor tree, like our 3, those stay inside your square root. So that's really what's happening there, is when we find that pair set of numbers, you're finding what is the value that's getting squared and pulling it outside your root. Now from here I always want to reduce my fractions, and these are reducible because they have a common factor 2. And so I can go ahead and break up my division, right? 2 would be divided by 2. This 2 root 3i would also be divided by 2, right? I have an overall big fraction. We can break it into the 2 separate ones. And then reduce each piece. So I would get 2 over 2, which is 1. My 2 over 2 would also reduce to a 1, leaving 1 times the root 3i. So that would be our reduced answer. That's the final answer that we're looking for on this particular problem. Let's look at problem 11. So problem 11 is falling under what we call those rational expression problems, or a rational expression section. And so rational just means we have fractions, right? So clearly I have fractions. And the expression part means I don't have an equation, right? Like on the last problem I worked out, I had an equation. There was clearly a left and right hand side to my equal sign. We don't have that here. So we kind of lose some of the tricks that work for equations because I don't have, you know, a right hand side to balance my equation with. So we have to be a little bit more careful. So if I look at this, I'm wanting to divide my 2 fractions. So in general, how do you divide 2 fractions? Well, you keep the first fraction as is, and then to perform that division, we change that to multiplication, but I have to compensate, right? You know, I've changed the operation, so what's the equivalent of this division by this fraction? It's multiplication by this reciprocal fraction. So I want to flip or reciprocate this second fraction. So that's essentially what happens is when you're dividing 2 fractions, it's equivalent to the multiplication of the reciprocal of your denominator or second fraction in your setup. So I've technically dealt with the fact of the division, but I want to go ahead and perform this multiplication and potentially simplify my result. So I could, you know, multiply these, you know, the tops and the bottoms. That's not going to help me. It's just going to give me more complicated polynomials that I'm then going to have to factor. So what we can do is take what we currently have and factor it first and see if there's common factors that will cancel, get rid of those, then worry about multiplying, you know, across the numerator and across the denominator. It's just going to save us so much work to do it that way. So this first fraction, in the numerator, I see 4x squared. And, you know, maybe I'd realize like, oh, that's a monomial, I can't break it down. But you technically can. You can break down the 4 into its factors. It's 2 times 2. And x squared is x times x. And here, if you like seeing things cancel out, that would be kind of really the way to go. Because if you notice, there is a 2x in the denominator. So by writing out my 4x squared that way, I can see that there's a 2 and an x that are going to cancel. So these monomials, you technically can factor them. Now on the denominator, I have x squared minus 16, so that's what we call the difference of perfect squareds. I have x, which is squared, and 16, which is a perfect square number. It's 4 squared. And so that has a very systematic, I guess I would say, a factoring pattern that you just essentially write the numbers prior to what they were to squaring, so x and 4, x and 4. One factor will need to be positive and the other negative. So it's kind of like a formula or a pattern that we use to factor that. Similarly, on my other fraction over here, this is a difference of cubes, and difference of cubes also follows a pattern. That one's maybe not as straightforward. So here I'll write both of them out. So for squares, right, difference of squares, if you have something squared minus something squared, that factors to the 2 binomials, one with a positive between the 2 values and one with a negative. But we could also have the cubes pattern. And for cubes, you would have something cubed minus or potentially plus, right? There's also the additive of cubes. Squareds, you only have the difference. Cubes, you could have cubes being added or cubes being subtracted. It works both ways. So here, because it was subtraction, we'll look at the subtraction pattern. So this fits that pattern, right? My A, so to speak, is the x, and my B, if we really look at 64, it's actually 4 cubed. So 4 also happens to be the B value. And so the pattern, how it works is you're going to have a binomial and a trinomial be your two factors. The binomial, you'll keep the A and the B and the sign between them. But then for the trinomial, the first term is your first value squared. The last term is your last value squared. And then the middle term is those two values multiplied, so A times B. And then here, since I have a minus, I'm only allowed one negative sign in this whole setup, and I've used it. So by default, both of these need to go positive. And to give you a sense, there's the additive pattern too, right? There could have been A cubed plus B cubed. So it fits that same pattern. You leave the values essentially without the cubes and with the same sign. And then the trinomial is the first value squared, the last value squared, and then the middle terms multiplied. And where my negative, right, I said only a single negative can apply. That single negative will always go either to in between the two values or on the multiplication of A times B. So for us, we only need the subtraction pattern. We don't need the addition. So I'll go ahead and erase that because we don't really need it. I just wanted to comment in case you did see the addition pattern, what happened there. And so let's go ahead and factor that. So we know our pattern, the A is acting kind of like X, right? And B is our 4. So there's my binomial. My trinomial would be X squared, 4 squared, and 4 times X with a positive sign. So that's essentially it. One thing I might notice is I can simplify it a little bit because of the 4 squared. So 4 squared, it might be better to actually write it like a 16. So I'll go ahead and change that. And then 2x I can't do anything with. I'll leave him alone. So now I factored everything. And typically when we're dealing with these rational expressions, that's going to be one of your steps typically is to factor everything. So then you can cancel out common factors. So I do have some common factors. I have x minus 4 in common, so that can cancel out. I also have a value of x that can cancel. And I also have a value of 2 that can cancel. And so once I'm certain I've canceled all of my like factors, then I can go ahead and do the multiplication across the numerator and across the denominator. So in the numerator I have 2 times x times this trinomial. And I want to write my trinomial in parentheses because I technically haven't multiplied anything, right? I'm just multiplying the 2 times the x piece because we can write it with them just right next to each other, but I'd have to distribute that 2x if I really wanted to multiply it to the trinomial. Then on the bottom, all that's left over is this x plus 4. So that would be one way to write the final answer, and I'm fine writing that way because on the homeworks you guys got very accustomed to leaving your answer in the factor form, and that's fine. However, if you did distribute your 2x through to perform the complete multiplication on the top, I'd still accept that. So the alternative answer if I did distribute would be 2x cubed plus 8x squared, and 2 times 16, that's 32x, all over x plus 4. So either one of those on the purpose of an exam would be fine. Okay, problem 12 is also a rational expression, also division. So let's see if we can follow through the same steps that we did for problem 11 previously. So the first thing I need to do is tackle my division. So I keep my first fraction the same and then multiply by the reciprocal or flip of my second. So this would be times with 6 on top and 2x plus 4 on the bottom. So I've dealt with the division part. Now we need to factor everything and see what factors will cancel. So when I factor the x squared minus 6, or pardon me, minus x minus 6, it's a trinomial, so it's going to factor into two binomials. We know x times x will get us the first term, the x squared. And then I need factors of negative 6 that would add to a negative 1x here. So I could think, okay, 6 and 1, no, that's not really going to get me the 1. I could maybe get a negative 5 out of that. What else could I try? 3 and 2. Ooh, 3 and 2 might work, right? If we put the sign in the right place. Because I want my result to be negative. So one of these factors should be positive, one should be negative. If I put my plus sign on the 3 and the negative sign on the 2, I get 1, but the sign would be all wrong. It'd be positive. So when something like that happens, I know that I'm close to the right value, but we just need to switch the signs. So if I let 3 be the negative factor and 2 be the positive factor, then those add to the negative 1x that we want. So that's using what's called the guess and check method, but there's other ways to factor this potentially too. Ultimately though, we're going to get to that same factorization. Now the 12, I could leave it alone or I can factor it. And I can tell you right now, I'm looking at the 6, and I'd really like to cancel a 6 out of my 12. So I'm actually going to break down my 12 as 2 times 6. Although we could break it down other ways, even down to its prime factorization. I want the 6 to match so we can cancel it. So that's why I would break down the 12 that way. Then for the 2x plus 4, I can factor that because they both share a factor of 2. So I can pull out the greatest factor of 2 and be left with x plus 2. And then now that everything's factored, I can go ahead and look for common factors on the numerator and denominator that will cancel. So x plus 2 could cancel out. My 6's, I already knew were going to cancel out. And then the rest I can't. There is a 2 on both of these, but they're both in the denominator. You need a numerator-denominator pair, so those don't cancel. So what is left from all this? Well, in the numerator, the only thing left is x minus 3. On the denominator, I would multiply 2 times 2, which is 4. And so I could leave my final answer like that. Technically, I could divide each term by 4 and think of this as 1/4 x, or x over 4, minus 3 over 4. And that's really equivalent. So either one of those would be mathematically correct answers either way. Okay, problem 13 is another rational expression problem. This time, though, I want to subtract two fractions. And subtraction of fractions, even addition of fractions, we need something to perform the actual operation. And what we need is a common denominator. And we can see right here, these are not the same denominator, right? They are definitely different. So how do I get a common denominator? Well, one thing that I want to know is what really are the factors that are hidden inside these algebraic statements. Because maybe they actually do have more in common, and we don't need to actually multiply like this whole second fraction by the 6x plus 3, and this whole first fraction by 2x squared plus x. So we don't want to have to do like a big algebra calculation if we don't really need to. So the trick here is to go ahead and factor the denominators and see what really is in the bottom there. So in the first fraction, there's a greatest common factor of 3 that I can pull out, and that would leave 2x plus 1. On my second fraction, I could pull out a common factor of x, leaving 2x plus 1. So when I'm looking for my least common denominator, I can already see they do have some things in common, right? They already have 2x plus 1 in common. So I don't have to do anything to adjust these fractions. They already match in that sense. This first fraction has a 3 that the second fraction doesn't. So I would need to include that multiple of 3 onto this second fraction. And then the second fraction has an x that the first one doesn't. So I'd have to include an x on the first one. So my least common denominator is actually all 3 of those multiplied. It's the 2x plus 1 factor times 3 times x. And I could multiply it all out and get the algebraic statement, but there's no advantage to doing that. It's actually better to leave it in the factored form because maybe later on stuff will cancel, right? So there's no advantage to multiplying it out and then factoring it later on. We can just leave it factored. So that's my LCD. In terms of my fractions, I'm really only including the factors that I need to get these denominators to match. So in the first fraction, it was missing the x, so I multiplied by x over x, essentially to make sure that I'm not fundamentally changing what was there, right? X over x is 1. Any number or statement, even this thing, if I multiplied it by 1, won't change its value. And that matters, that we don't want to change the value of what's there. We just want to have it include that extra factor of 3. Same idea over here. I did 3 over 3 because, again, that would be 1. And multiplying our statement by 1 won't change it. So let's see what comes out of this. So on the top, I'm multiplying x by a binomial. So that's really, honestly, a distribution problem, right? I distribute x, getting 2x squared. Distribute the x to negative 5, getting negative 5x. And this would be all over all this stuff. 3x times 2x plus 1. My second fraction, I multiply the 3. And that's also over 3x times 2x plus 1. So now I have that common denominator, right? The denominators match. So now I can actually do the operations across the numerator. So it's this 2x squared minus 5x minus 3. And I can write it as one big fraction as well over the same common denominator. Now before I say, yay, it's my final answer, I'm done, we're always trying to simplify fractions. Well, how do I simplify this fraction? I need to cancel out any or common factors from the numerator and denominator. Well, I know the factorization on the bottom, but now I created this new trinomial. I don't know what its factors are and whether those might match something on the bottom. So I need to factor the numerator too to see if I can cancel out any of those common factors. So it's a trinomial, so it's going to multiply, or pardon me, factor to two binomials. And this particular type of factoring is tricky because of the 2x squared. So there's actually two ways to do it, and I'll briefly show each one. So one way is to kind of use that similar guess and check method where you're placing the factors into kind of the 4 slots to get the 4 parts of FOIL. So 2x times x gets me the first term, 2x squared. Then I want factors of negative 3. Well, I know I got to use 3 and 1, and one of them needs to be negative. So I'm just going to place the values and see what comes out, whether it works or not, or we have to adjust. So how do I know if I need to adjust? Well, I need to check the outer and inner terms, essentially, from FOIL. So if I multiply the outer set of terms, I got 2x. If I multiply the inner set of terms, that's negative 3. When you combine those, I get a negative 1x, not the negative 5. So I know something's wrong. Well, one easy fix might be to try and make my 3 the negative and let 1 be negative and see what happens. And see if that fixes it or if there's more to do. So if I did that, the outer set would get me negative 2x. The inner set would get me 3. Oh, no, that's just positive 1x. So what that's telling me is the numbers themselves aren't in the right location, and that's why I'm not getting the 5. So how could I adjust that? Well, I could go ahead and change these positions. Here the positions actually do matter because this is 2x, not a single x anymore. So where I position the factor will affect the result. So I had the 3 on the left. Now let me try the 3 on the right and see if that helps. And we'll try negative 3, positive 1, see if that works. So again, I try the outer inner terms, see if it gets me the negative 5x that I want. So the outer set gets me negative 6x, the inner set gets me 1x, and what do you know, I finally found it. It's negative 5x. So that's partly why this method is called guess and check, because you're really guessing at what the factors need to be and where they need to be located, and then you're checking essentially kind of like by refoiling it to see if you get back the values from the original trinomial. So I found the factors. Now that's not the only way to do it. There's also what's called an AC method, and then there's also the method that was shown in the pre-class videos, and I kind of like that method, and I think some people might like it as well because it takes the guesswork out of this. And that's the problem with this method is I did a lot of guessing right there, and sometimes, especially if the numbers get big, finding those guessings for factors is really hard. So something that can take the guesswork out is kind of nice. So how does that method work? Well, it's called the magic X method in the video. And how it works is you create an X, and that X is really just organizing your work. On the top of the X, you multiply your A and your C term. So 2 times -3 is -6. And then on the bottom of my X, I write the X coefficient -5. So I want to find the 2 factors of -6, and I'll write them in these other sides of the X, the 2 factors of -6 that add to -5. Okay, well, what would work there? Oh, how about -6 and +1, right? But if you notice, those were not the numbers that I put right here. So this method, we have to do some adjustment. So the 2 numbers you find, you still have to divide them by your A, or the leading coefficient. So I have to divide by 2, take this guy, divide by 2, and then reduce the fractions, right? We want to reduce them. So -6/2 reduces to -3/1. 1/2 doesn't reduce. And so right now I've actually found all the values from our factorization here. So the number on the bottom, right, the 1, represents the 1x that we have right here. The number in the numerator, the -3, represents the other value, right? So the denominator gives you the coefficient of x, the numerator tells you the other value. Same idea here. 2 would be the value of x, the coefficient of x. 1 would be my other value. So that's another way that you could factor it as well. And there's, you may be using currently a different method too. That's fine. Ultimately, we need to know how to factor this type of trinomial. That's really the big thing. So this was 2x plus 1 and x minus 3. Okay, so we have everything factored, and thankfully our work paid off. We do have a common factor of 2x plus 1 that we'll go ahead and cancel. So then in the numerator I'm left with x minus 3. On the bottom I'm left with 3x. We might be tempted to cancel out our x's or say the 3's. However, on the top it's x minus 3, right? This is not pure multiplication, this is subtraction. And you have to have pure multiplication to cancel things. So this minus kind of throws that possibility out of the window. So that's the best we can do. Okay, 14, more rational expressions. I'm adding my rational expression, so similar to the previous problem, 13. We need a common denominator before we can add or subtract fractions. And I definitely do not have a common denominator, right? Our denominators do not match. Well, how do I get a common denominator? We gotta factor the denominators and see what really is there, right? What do they maybe have in common as a factor already? And what do they not have in common? So that's the trick here. We want to factor these denominators. So I'm going to factor my first denominator. I better actually give myself some more room here. And so my trinomial will factor to the 2 binomials. And then I want factors of -8 that add to 7. I know +8 and a -1 will do that, right? 8 times -1 multiplies, gets me -8. 8 minus 1 gets me the 7 for the x that we want. Then we do the same sort of process on the second trinomial. So factors of 2, +2, that could add to a -3. So to get things to multiply to be positive but add to be negative, you need 2 negatives. Factors of 2 that could add to 3 are 2 and 1. So I have my factorization. Now I can look at my LCD. So the LCD is going to be any factors they have in common, like they actually do have this x minus 1 in common. That would be technically part of my least common denominator. And anything else they don't have in common too. So x minus 8 would be also part of my LCD. So would x minus 2. So that would be the ideal denominator, or at least common denominator that we want. Right now those don't match that. So we need to multiply to these fractions anything any factor that isn't there that we need. So in this first fraction, I'm missing the x minus 2. So I need to include an extra x minus 2 on the top and bottom, essentially multiplying by this. This is really a 1 in blue. So that's a 1. So multiplying by 1 won't change what's there. It just gets the x minus 2 factor that we want included. Then on the second fraction, I'm missing x plus 8. So we want to do the same thing, x plus 8 on the top, x plus 8 on the bottom. And now we need to figure out what these numerators actually are. The denominators we know, right? It's going to be those same 3 factors, what we identified as our least common denominator. And here the ordering doesn't really matter, right? They're all 3 multiplying, so as long as we have the same 3 things multiplying, they're the same. So for my first numerator, I need to go ahead and distribute my 3 into the binomial of x minus 2. So 3 times x gets me 3x. 3 times negative 2 gets me negative 6. Then similar idea for the 2, that needs to distribute into the x plus 8. So I get 2x. 2 times 8 gets me 16. And now I have 2 fractions that do have common denominators, right? They share the same common denominator, so I can actually perform the addition across the top. So I could make this one big fraction with that same common denominator. And across the numerator, I would have 3x added with 2x, so that's 5x. And negative 6 added with 16 becomes 10. And then again, I want to see if this 5x plus 10 has a common factor or any sort of factor that might cancel with our denominator. So I'd try and factor that. I can. There's a common factor of 5. And I get x plus 2. And I might be tempted to cancel with the x minus 2, but they don't really match, right? They really don't match. So really, I didn't necessarily have to pull out that 5. It didn't do anything for us, right? It didn't allow us to cancel anything. So in this instance, I would be fine with either the factored answer as your final answer, or in an instance like this, when you factor it and stuff doesn't cancel, you can just backtrack a step to what you had prior to factoring and choose that as your final answer. So either one of those would be perfectly fine as a final answer on the exam. All right, 19 is a compound inequality. So why do I say it's compound? Because there's 2 inequality statements that we're trying to satisfy. I want this whole algebraic statement to be greater than 0, and at the same time, this whole statement to be less than or equal to 3. So we want to satisfy both of those. So in inequality, we said you solve it just like an equation. Any operation you do to solve a linear equation, you can do here. And that's still true. However, it's not really like I have a left and right hand side with the inequality symbol kind of taking the place of the equal sign now, because now I have 3 pieces. And so what we can do on this compound inequality is still solve it like an equation, but any operation I do to try and isolate x in the middle, we have to balance that operation by performing it to the left inequality and to the right. So it's the same idea of balancing equation, but now we kind of have 3 parts that need a balance. So how would I try and solve this? Well, the first big thing that's just blaring me in the face is I have a fraction. I have division by 5, and we don't like fractions. So here, just like with equations, inequalities allow us to get rid of those denominators or fractional pieces very easily. You just multiply by your denominator. So I want to multiply this guy by 5. And if I multiplied, or let me actually write the 5 out on this other side so we don't think it's like a 5th power. So if I multiplied the middle by 5, then I have to multiply the left by 5, and I have to multiply the right by 5. So that's what we mean by balancing all 3 pieces. So let's see what comes out of that. So 5 times 0 gets me 0. The 5 that got multiplied in the middle will go ahead and cancel out the 5 in my denominator, which is nice. I'd be left with negative 2 times 3x plus 4. And then 3 times 5 is 15. So now I have a choice here. I could distribute my -2 through and then continue solving. Or, I can acknowledge I don't really want this -2 here, right? I want to get rid of that nonetheless. So I could choose to do the opposite of multiplication and perform division. So either way that you take it there, either distribute the -2 and continue on, or divide out the -2, you'll still eventually get the correct final answer. So you could do it either way. I think most students would probably distribute because we're really well trained in doing that, right, after all these polynomial examples. And so that's the way I'm going to work this. But if your intuition was to divide out -2, that's fine. You could do that. So let's see. If I did distribute, I would get -6x. -2 times 4 is -8. And then we would need to continue solving and isolating our variables. So I don't want my -8, so the opposite I would have to perform to get rid of my -8. So that's adding 8. So 0 added to 8 on the left is 8. The middle part, I'd be left with -6x. And then on the right side, 15 plus 8 is 23. And then last but not least, I don't really have x by itself. I have this -6 in there. So I could go ahead and divide out -6. And I may have some fractions that need to reduce. So 8/6, they do share a common factor of 2. So I could think of kind of dividing each one out by 2. So I'd be left with 4 over 3. And because I have this negative sign, this overall thing is negative. My -6 would cancel, leaving x in the middle. And then 23 divided by 6, I don't think that actually reduces. But here's how you can tell. I think I mentioned a couple different times in class, all your scientific calculators that I recommended for you guys to buy, they allow you to reduce fractions. So you would type in your number, get the decimal, and then it's different on every calculator, but just know the series of keystrokes that you need to get from that decimal back into a fraction. And the nice thing about your calculator is it always converts it back to a fraction in lowest terms, which is awesome. So here I plugged it in to see if it actually would reduce, and I got back the same fraction. So that's telling me it won't reduce. And in fact, I think 23 might be prime. So I don't think there's any way that you'd have any factors at all reduce. So the best I could do is write this as 23/6, which is negative. And wait, is that right? Let me go back and look. So 15 added 8. Yeah, that's 23. Okay. I want to make sure I didn't make a mistake there. Now here's the thing. I divided by a negative. And so that's the one of the instances where inequalities are not like equations. That if I multiply by a negative number in my solving steps, or if I divide by a negative number in my solving steps, we have to compensate, right? Because think about it. I had a +8 and I got this -4/3 result. I had a +23 and I got this -23. So just like the signage of our numbers change from positive to negative, our inequalities need some adjustment to deal for that change of signs as well. So we flip our inequality symbol when you multiply or if you divide by a negative number. So I'd go ahead and flip this first symbol and flip my second symbol. And then the problem here is my inequalities aren't really facing the right way. And if you look at this, what was the decimal that we found on the calculator here? It was -3.8, and if you compare that to -4/3, right? Sometimes it's hard to know which one's bigger or smaller. So my 23/6, that's actually a lesser number compared to the -4/3, and that's not kind of the way that's written right here. I have the bigger quantity on the right and the smaller quantity on the left. So when I flip those inequality symbols, kind of the natural ordering of having the least value on the left of your inequality and the greatest on the right got all mixed up. So how do I fix that? Well, I can go ahead and rearrange this inequality. I'm going to put the -23/6 on the left, right? Because that's the lesser number compared to -4/3. And my x is still in the middle. And then because I rearrange this, I want to make sure that my inequality symbols are still meaning the same thing, or opening appropriately to mean the same thing. So for this first symbol, when I compared x and the 23/6, the x was the greater quantity, right? Our inequality opened to x. So I want to do the same thing here, right? Essentially making sure that it still has the same meaning. X is greater compared, right? X is still greater compared. Now when I do the same thing over here for -4/3 and x, it's showing that 4/3 is going to be greater, right? It's opening to 4/3. So I want to do the same thing there. So I had to kind of rewrite it that way. And we'll see when we write our solution with graphing on the number line, that really is helpful to reorder it that way. So anytime you divide by a negative number, kind of see, do you need to adjust the way that your inequality is written to get the meaning appropriate, right? Where the smallest values on the left and then the largest values on the right. Because then graphing things on our number line and doing our interval notation, those will both be a lot easier. So what are the 3 ways that I can write my solution? So one way is in set builder notation. And you do the little curly brackets for a set. You would state your variable. Here it's x. We do the little line, that means such that. And we're just going to rewrite the same answer we had before. -2/3, or pardon me, -23/6 is less than or equal to x, which is less than -4/3. And then you have to close off your set with a curly bracket. So that's set builder. Then I would go to graphing on a number line next. So I would draw myself a number line. Any important values we include on that number line. So I want to include -23/6. I'm going to put that towards the left because we know that's smaller than -4/3. And just like our compound inequality shows x is in between, same idea here. My solution is going to be in between those two. So I would shade that section of the number line. For the 23/6, it's allowed the option to be equivalent. So we show that with a bracket or a filled in dot, right, on the number line. And then -4/3, I don't have the equal to option. So we show that as a parenthesis or a dot that isn't shaded on our number line. So that's our graph on the number line. And then lastly, we would do the interval. An interval is a lot easier once you graph it because it mirrors the graph to number line pretty well. So here, kind of on the left, we wrote the least value for our interval. Same idea. I'm going to write the least value, -23/6 on the left. This guy got a bracket because I'm allowed to be equivalent. I would also use a bracket for the same reason, right? We can be equivalent to the -23/6. Then you put the greatest value in your interval on the right. So my greatest value is -4/3, and I used a parenthesis. I also get to use a parenthesis. So that would be how we solve our inequality and write our solution the 3 different ways.